Hello and welcome to the 2022 Nobel Prize Lectures. This event is brought to you by Simon Fraser Faculty of Science. Before we start, we would like to acknowledge that we are on the unceded territories of the Musqueam, Squamish, Tsleil-Waututh nations. We thank them for having cared for these lands and waters since time immemorial and look forward to working with them in partnership as we continue to build this great region together. We hold this event every year to celebrate the Nobel awardees and their impressive research work and allow our community and friends to engage in meaningful conversations with our university faculty members about research. Tonight, we recognize the contribution of the 2021 Nobel Prize awardees in chemistry, physics, and medicinal chemistry, medicine and physiology. Experts from these fields will highlight the impact of these prizes and the connections between fundamental and applied research. My name is Dr. Nabil Merbou from Simon Fraser University Chemistry Department, and with me as co-host this evening is Stuart McNeish from Oh Boy Productions. Hello, Stuart. Thank you for helping us with this event.
Well, thank you, Nabil. It's my pleasure to be here. I'm always pleased and honored to be a part of this celebration of science and research, and to be able to engage with the faculty presenters who are with us this evening. It's important that SFU stages this event every year, and it's a fitting opportunity for the general public to learn more about science research, the Nobel awardees, and their impact on our everyday lives. I'm excited to learn more about these contributions. So a warm welcome to all of those of you who are joining us virtually this evening. We have an impressive number of enthusiastic viewers who are tuning in, and we want to thank you for your interest in this event. To help keep this event interactive and allow you an opportunity to participate, we have a question and answer field on the right-hand side of your screen. We encourage you to type in any question or comment about the discussion and presentations. In addition, we will have time at the end of the presentations to read those questions out to our faculty. On another note, we will record tonight's event for others to view later, and SFU's Faculty of Science will share the material. The organizers will also send out an online feedback survey to all of those who attended tonight. And we encourage you to fill them out because we appreciate receiving your comments and suggestions so that we can continue to improve and expand the quality of this incredible series. Nabil?
Absolutely, Stu. We would love to hear from you, your thoughts and ideas. Please send your questions and comments on the right-hand side of your screen. We truly appreciate your participation this evening. We also want to thank Oh Boy Productions for helping us bring this event live to you while following all the COVID-19 safety protocols in studio. Tonight, we're happy to have three faculty members from Simon Fraser University present this year's Nobel Prize awardees and their research. We are thrilled to be able to stage this virtual event with them.
Before we move on and introduce our faculty presenters for this evening, we would like to hear a few words from the Dean of Science Pro Tem at Simon Fraser University, Dr. Michael Silverman. Unfortunately, Michael cannot join us physically in the studio tonight, but he has pre-recorded some befitting remarks to help us begin our presentation. Let's now hear from Dr. Silverman, the Dean Pro Tem of the Faculty of Science at SFU. Michael.
Thank you, Stu, and thank you to all of you who are joining us for this special virtual event. SFU Science is delighted to present our annual Nobel Prize lectures. The purpose of the Nobel Lectures is to reflect on and give insight into the work of the winners of the 2021 prizes in physics, chemistry, and medicine or physiology. Each reflects profound advances in science that have substantially impacted our world. Tonight, you will be hearing from three of SFU's leading researchers who will bring to life the discoveries recognized by these prizes, highlighting the enduring impact of their science on our global community. Some of you in the audience today might be aspiring scientists, perhaps in a field similar to one of tonight's experts or in a different discipline. If you decide to pursue scientific knowledge and expand your understanding of our world, you will find an incredible community of professors, researchers, and students at SFU's Faculty of Science. Our programs are designed to inspire students to make real-world changes by partaking in research projects in the lab or field, or by participation in a co-op work term with a company or government agency, and ultimately making a difference in our communities. If you would like to learn more about studying science at SFU, I encourage you to connect with Claire Wilson at science_recruiter@sfu.ca, who can answer any questions you have. Lastly, I want to thank our presenters for taking the time to participate this evening and shedding light on these incredible scientific discoveries. And thank you to Oh Boy Productions for assisting us in staging this event. And most importantly, thank you to our SFU alumni and donor friends, science students, and SFU faculty and community partners for joining us. I hope that you will enjoy this event.
Thank you, Dr. Silverman. We always appreciate opportunities to engage with the public on science research at SFU. And now let's introduce our three faculty presenters who are with us this evening in the studio. First off is Dr. Rob Britton from the Chemistry Department at Simon Fraser University. Dr. Britton completed his PhD at UBC with Professors Edward Piers and Raymond Anderson in 2002, studying natural product isolation and synthesis. He was then an NSERC Postdoctoral Fellow in Cambridge, working with Professor Ian Paterson and on the synthesis of complex structure from marine biology. Rob then joined the Merck Process Chemistry Group in Montreal before beginning his independent research career at Simon Fraser University in 2005. He is currently a professor at SFU, leading a research program focusing on reaction discovery, natural product synthesis, medicinal chemistry, and radiopharmaceutical chemistry. Rob?
Hi, everyone, and to all our virtual viewers tonight, welcome.
Thank you. This evening, our next presenter is Dr. Edgar Young from the Department of Molecular Biology and Biochemistry. Edgar Young is an associate professor in the Department of Molecular Biology and Biochemistry at SFU. His research investigates ion channel proteins and their structure switch in response to electrical and chemical signals, producing complex cardiac and nervous system behaviors. Edgar, welcome.
Hello, everyone. I'm really excited to be here tonight.
Our last faculty presenter for this evening is Dr. Kirsten Zickfeld from the Faculty of Environment at Simon Fraser University. Dr. Zickfeld is a distinguished professor of climate science in the Geography Department, which she joined in 2010. She holds a PhD in physics from the University of Potsdam in Germany. Dr. Zickfeld's primary research interests are in the long-term effect of human activities on climates. Her research on the irreversibility of human-induced climate change and carbon budgets consistent with climate targets. Dr. Zickfeld's work is internationally recognized. She has been honored with many prizes, among those the President Prize in the Canadian Meteorological and Oceanographic Society and the SFU President's Prize for Leadership in Sustainability. Kristen?
Thank you, Nabil. It is a pleasure to be here tonight, and I look forward to the discussion.
Thank you, Dr. Zickfeld. Again, at this point, we would like to remind all of our viewers who are joining us virtually that we do have a question and answer field on the right-hand side of your screen. And we would love to receive any comments or questions about the discussion and presentations. And at the end of all three presentations, Nabil and I will have time to read those questions out to our faculty. Thanks for your participation. Nabil?
Sounds good, Stuart. Let's begin with our first presenter, Dr. Rob Britton, to present the Nobel Award for Chemistry and the outstanding work of Benjamin List and David Macmillan. The catalysis of chemical reactions has historically relied on expensive and often low-abundance metals such as gold, palladium, and platinum. However, the discovery that inexpensive and naturally occurring organic molecules can catalyze the same reactions has caused a fundamental change that has led to more environmentally friendly and economical processes and synthetic tools for scientific discovery. Friends, let's listen to Dr. Rob Britton to learn more about these beautiful reactions. Rob?
Thank you, Nabil. Again, I'm really happy to be here today, and I'm really happy to present the research that went into the discovery of the asymmetric organocatalysis. And this is the work that was awarded the Nobel Prize in 2021 in chemistry to Benjamin List and David Macmillan. So before I start, though, I think it's important to try and explain what these two words, asymmetric and organocatalysis, actually mean, because these aren't words that we commonly come across at home or in our workplaces. So I'm going to begin by just talking about these two different words, what they mean, and how asymmetric organocatalysis came about, and some of the impacts of this work. And then I'll try and finish by just describing a little bit who these people are, both Benjamin List and David Macmillan. So when we think about symmetry, we often, we can clearly think about objects in nature that are symmetrical, and we can think about something like this butterfly here. And if we put an imaginary line down the center of the butterfly, we would know that both sides of this butterfly are the same. And essentially, this is a symmetric object. There's other types of symmetry, though, and one other one would be a mirror image symmetry. And here, for example, would be the mirror image of this butterfly. Now, in chemistry, what we sometimes become concerned with is whether the mirror image is superimposable or not on the original object. And in this case, you could see the mirror image would be superimposable on the original object. Now, a good example of something that is not superimposable on the original object is our hands. We have a left hand and a right hand, and we know that these are mirror images of one another, but they are not superimposable. And so in chemistry, when we deal with molecules that are not superimposable, we call those molecules chiral molecules. Now, I've just shown at the bottom of this slide two examples of chiral molecules. So these are two of the mirror image versions of the amino acid alanine. And on the left-hand side, we have one that we call D-alanine, and on the right-hand side, we have one that we call L-alanine. And in chemistry, we call these mirror image molecules that are not superimposable enantiomers. And these molecules have all the same properties. So same melting points, same polarities, solubilities, unless they're placed in a chiral environment. And that's really critical. In a chiral environment, they will behave differently. And one thing you might note is that in nature, or in our lives, we generally only come across one of these enantiomers. So if you go to a health food store and look for an amino acid supplement, you will not find D-alanine, you will find L-alanine, because most of life relies on this amino acid. And this is quite important because, I'll just point out that the central carbon of these amino acids is what we call an asymmetric carbon, and that's where this word asymmetric comes from. So it's the central point of these chiral molecules. So the fact that life relies on one of these amino acids, this L-alanine, means that the proteins that are made of amino acids are also chiral molecules. And this is really important. And so you can think about when a molecule interacts with a protein, it can select then for one of these mirror image molecules. And the best way to imagine this is by thinking of a protein like a glove, and think of the molecules as your right and left hand. And you could imagine that only one of your hands, in this case, the right hand, would fit in this right-handed protein. And so this might seem a little bit abstract, but I'll try and contextualize this for you. So if you, in nature, we have many mirror image molecules that exist. And because our proteins create a chiral environment, they interact with these molecules in different ways. And we sense them then in different ways. And a really good example of this is the molecule limonene, which exists in nature in both enantiomeric forms, or both mirror image forms, which we could call L-limonene and D-limonene. Now, if you smell L-limonene, it's the smell of a lemon, whereas its mirror image form interacts with different proteins in our olfactory system, and it smells like an orange. And this is really interesting, but maybe not something that is critical to our to advancing chemistry. Where it does become more critical, though, is in drug discovery. And so here I've shown two mirror image forms of the drug thalidomide. Now, the molecule on the right turned out to be an excellent sedative and was developed in the late 1950s for this purpose. And in particular, it was used to treat morning sickness in pregnant women. Now, unfortunately, this was sold as a mixture of these two enantiomers because they're very difficult to separate. And the molecule on the left the S version, or mirror image thalidomide, actually had very detrimental teratogenic properties, which means that it led to birth defects. And there were more than 10,000 babies born with birth defects because of the fact that both of these enantiomers were used together in this drug. Nowadays, about half of all of our drugs are chiral molecules, so one or the other mirror image of a molecule. And these molecules are generally sold as single enantiomers because of this problem where with the mirror image form potentially having negative effects. So a long-standing challenge to chemists then is how can we create chiral environments so that we can selectively make one of these enantiomers over another? And in 2001, a Nobel Prize was awarded in the area of asymmetric synthesis, or this production of one enantiomer of a molecule over another. So the other word in this year's Nobel Prize, or the 2021 Nobel Prize, is organocatalysis. And organic just comes from the chemistry of carbon compounds, which include things like amino acids, peptides, DNA, and proteins. And catalysis comes from catalyst, which is just a molecule or a substance that can increase the rate of a chemical reaction, but does not get consumed in the reaction. And this graph at the bottom kind of shows that where we have a normal pathway or an uncatalyzed pathway in red, which requires much more energy than the catalyzed pathway. And you'll see that the catalyzed pathway may have more steps, but overall requires much less energy, and so those reactions go much faster. And a good example of this would be the hydrogenation of alkenes, which would go too slow to even measure the rate of the reaction without a catalyst. So when we think about catalysts and we look to the periodic table, and there's obviously many elements in the periodic table that we could think of using as catalysts. And what it turns out is that these elements in the middle of the transition metals, so rhodium, iridium, ruthenium, platinum, and palladium, turn out to be some of the best catalysts for many of our organic reactions. Now, one of the biggest problems here, as you can see from the prices I've shown on this slide, these are also some of the most expensive metals that exist because they're so rare. Now, if you want to use these in organic reactions, you also have to put ligands on these metals so that they can be solubilized and stabilized, and you often have to protect them from air and moisture because they degrade very quickly. Now, just if we want to think about an asymmetric catalyst, so a chiral catalyst or a chiral ligand attached to one of these metals, these now become very expensive. And I actually looked up the other day the cost of one of the more common chiral rhodium catalysts, and this costs $280,000 per ounce of rhodium in that catalyst. So a long-standing challenge in catalysis then is how do we move away from these expensive metal catalysts and find cheaper and more efficient ways of making chiral molecules? And I'll just point out that both in 2005 and 2010, Nobel Prizes were awarded for these metal catalyzed reactions. So this is still a very active area of research, but one that does present its own challenges. So now I'd just like to talk about putting these two things together. So what is asymmetric organocatalysis? And this actually began more than 50 years ago at two companies. So in one company, which was Hoffmann-La Roche in New Jersey, there was Hadjos in Paris. And at Schering in Berlin, there was Eder, Sauer, and Wiechert. And they were all looking at the same reaction. And this is the reaction I've shown here. And this is not important to understand this reaction in particular, but just to know that they were trying to make one of these mirror image molecules, starting from a non-chiral molecule on the left-hand side. And they looked at a variety of ways of trying to select for one of these mirror image molecules and eventually found that the cheap amino acid proline could catalyze this reaction and favor the formation of the molecule on the left. And the reason why they were interested in this, because at the time, there was a lot of interest in steroids as drugs for many different things. But in the case, in the molecule in the box here, you can see mestranol was a drug that was developed for birth control. And the molecule on the left kind of maps on well to the blue part of mestranol. And so they didn't want to form the mirror image of this molecule. So they're trying to find a way to select for the molecule on the left. And they found that if they used proline to catalyze this reaction, they actually favored the desired enantiomer or mirror image molecule 97-3. This was really an incredible discovery. So not only did they replace expensive metal catalysis with a cheap, readily available amino acid, they also found that it could create the molecule they wanted in really good yield and selectivity. And so in one of the publications from 1971, they also discussed how this could happen. And they stated that that supports, or the mechanism or the way this goes about probably involves the formation of an enamine on the side chain. And there's a lot of confusing words there, but I'll try and show this with pictures. So essentially what they're saying is the proline connects to the non-chiral molecule and makes something called an enamine. But now, since this enamine has proline incorporated in it, it's a chiral molecule. And so when it reacts, it can react in a way that can favor one of the two enantiomeric products. Now, also, it will reduce the energy required to reach those products, so it'll make the reaction faster as well. So in this case, you can see that if this molecule were to cyclize and form the second ring, these molecules are no longer mirror images from one another. I've just highlighted the area in these molecules that make them no longer mirror images. And because they aren't mirror images, they'll have different energies and different properties, and so you can selectively form one of these two. In this case, it selects for the one they wanted. Water can then remove the proline from the molecule and give them this building block that they can make steroids from. So this was really an incredible discovery and should have been the birth of organocatalysis. And this is a fantastic quote from one of the Nobel laureates from 2021, Benjamin List, who stated that somehow this chemistry fell asleep in a way. It was used occasionally here and there, and people had thought about the mechanism, but somehow they just didn't bring it together. And that's exactly what happened. Even as a graduate student, I learned this chemistry in the 1990s, but didn't think about ways that it could be useful. So by the late 1990s, other research groups began to use chiral organic molecules as catalysts. But often these were very complicated to make, required their own complex syntheses, and were really tailored for very, very specific reactions. So it didn't really lead to the birth of this field of organocatalysis. However, in 2000, Benjamin List published the first paper on an organocatalytic reaction. This is something called a proline-catalyzed aldol reaction. And I'll just show here a picture of this reaction. It's not important to understand how this happens, but you'll see that this involves the same catalyst that was used in 1971. Proline, a cheap, readily available amino acid. So in this case, the proline reacts with a ketone and forms a chiral iminium species, which can also exist as this chiral enamine. The chiral enamine can then react with the aldehyde and give the product that they wanted from this reaction. And in this case, they got 98% of a single enantiomer and only 2% of the mirror image product. And this was really a remarkable finding. I just picked out a quote from the paper and then a few quotes from Benjamin List about this discovery. So in the paper, it stated, this is the first example of a non-metallic small molecule catalyst for direct intermolecular asymmetric aldol reactions. So since then, Benjamin List had stated that it was actually also his very first independent experiment, which was really, really incredible. And also that when he did this first experiment, he was really nervous and insecure. He had this feeling that maybe it was just a really naive idea and that all the other chemists, the smart chemists, already knew there was no way this was going to work, but really this was the birth of organocatalysis. And I'll just point out that this paper was submitted on December 7th, 1999. So at the exact same time, another group in the United States, headed by David McMillan, published a paper on the proline-catalyzed Diels-Alder reaction. And in this paper, they actually coined the term organocatalysis. And I'll just point out that this paper was submitted just 31 days after the work of Benjamin List. So this was happening at the same time. It's a different reaction, though. So in this chemistry, McMillan was trying to carry out a Diels-Alder reaction, which involves a dienophile and a diene. Now, these two things don't react very well together, and so you need a catalyst for this reaction. And again, McMillan turned to a derivative, in this case, of proline, another cheap organic molecule. This makes a chiral iminium species, which is then rapidly reacts with the diene to give these two mirror image Diels-Alder products. Now, in this case, the selectivity wasn't fantastic, about 3-to-1. And so another additional bit of work that was included in this first publication by McMillan was the discovery of new organocatalysts. So they actually set out to make molecules that are like proline, but unnatural and may impart more selectivity on this reaction. And in the end, they found the molecule on the bottom right, called an imidazolidanone, was the most selective for this type of reaction. And just a quote from David McMillan, when they did the first experiment in this way, I really like this quote. He says, "I was just blown away that the thing even worked. I went into my office and started jumping up and down." So by the early 2000s, the field just absolutely exploded. So in 2005, there was about 150 publications every year now on new organocatalytic reactions or new catalysts for organocatalysis. By 2010, this is essentially now an established field of research. So we've gone from something 10 years earlier that really didn't exist to now close to 1,000 publications a year. That's 20 publications every week on this subject. So clearly, this is an important field of research. So I just want to talk a little bit about what the impacts of organocatalysis are. And I think one of the most important ones is the democratization of asymmetric synthesis. So as I mentioned before, this was normally something that could only be done with very expensive transition metals and expensive ligands. And now anyone who has a round bottom flask can take a carbonyl containing molecule like this one on the bottom left, react it with a cheap amino acid like proline, and form a chiral enamine or a chiral aminium species. And these can then go on to make very high value products like our pharmaceuticals, agrochemicals, and fragrances. Just to highlight this, the use of organocatalysis was recently reported to make this drug darunavir, which is an antiretroviral drug used to treat and prevent HIV/AIDS and is on the WHO's list of essential medicines. And this is essentially the same reaction that Benjamin List published much earlier, now with two aldehyde starting materials being combined in an aldol reaction, again, catalyzed by cheap proline. One other very important impact of organocatalysis is that it continues to inspire new discoveries. And this is maybe a plug for our own work at SFU, but we also work in this area of organocatalysis. And just a few years ago, we discovered a brand new reaction that allows us to make really important molecules known as nucleoside analogs that are critical for treating viral infections and for treating cancer. And so this is a really important aspect of organocatalysis, that it's turned into an entire field on its own with many different applications. So I'd just like to end by talking a little bit about these two Nobel laureates, just so you can get some insight into who these people are. So Benjamin List was born in 1968 in Frankfurt, received his PhD in 1997 at the Goethe University in Frankfurt, and his first academic position was in Southern California at the Scripps Research Institute, where he started in 1999, essentially the same year that he reported his first work on organocatalysis. Now he currently works at the Max Planck Institute for Kohlenforschung, and I thought it was interesting to note that his aunt has also won the Nobel Prize in physiology or medicine in 1995. And so I tried to find a really good quote from Ben List that might give you some insight into who this person is. And I really like the one at the bottom of the screen here, where he says that he thinks that a Nobel Prize is just too much for a couple of people. In reality, it wasn't just his lab, but the whole field. All these people who have worked very hard and very competitively and very aggressively, everybody who contributed to this field in the last 20 years should feel proud. And it wasn't just Dave and him. And I thought it shows just the humbleness of this exceptional scientist. So the other award, or the other Nobel laureate, is David Macmillan. He was born in the same year, but in Bellshill, Scotland. He received his PhD in 1996 from the University of California at Irvine. And his first academic position was just a 3-hour drive away from Benjamin List at the University of California in Berkeley. And so these two made their key discoveries just 3 hours apart as part of their very first or second year of research as independent academics. Dave Macmillan then moved on to Caltech in 2000 and is now at Princeton University. And a really fantastic quote from Dave Macmillan is shown here. The morning that he was notified that he won the Nobel Prize, he texted Ben List and said, "Somebody's pranking us. I bet you $1,000 is not real. I'm going back to bed." I thought that was really, really kind of telling. Another really great thing, the morning that he won the Nobel Prize, he sent a message to his group that saying, despite the recent news events, I think it would still be fun to keep subgroup at 9 a.m. this morning. So essentially he's saying, we're still going to have our group meeting this morning and continue on, and clearly showing what a dedicated, how dedicated he is to advancing the field of chemistry. And again, I want to thank you for the opportunity to talk to you all today about asymmetric organocatalysis, and I hope I've shed some light on what this award means to the field, and how important this work is to advancing our ability to make these important chiral molecules.
Thank you, Rob. Your enthusiasm definitely has shed light on it, these discoveries, and made them very interesting. Quite amazing to think of how these new scientific discoveries can lead us to even more environmental solutions. Now, just back to the back to you, the viewers. We appreciate those of you who have been submitting and typing in questions so far. We'll get to those questions and comments a little bit later, but now it's time to move on to our second presenter for more. Nabeel?
Thank you, Stuart. And thanks, Rob, and everyone for submitting their questions. Next, we have Dr. Edgar Young, who will be discussing the Nobel Prize in Medicine and Physiology. The 2021 Nobel Prize in Physiology and Medicine was awarded to David Julius and Ardem Pataputian for the discovery of key receptors in our nervous system that enable us to sense heat and touch. In this talk, we'll see how these ion channels work as electrical switches to convey sensations of pressure, pain, heat, and cold, and we'll explore the prospects for medical benefits. Edgar?
Hello. Well, as you heard in the introduction, we'll be discussing the sense of touch. Now, you probably have all learned about the 5 senses, and you might notice that 4 of them, sight, hearing, taste, and smell, are all gathered together in one part of your body, like up here. But the 5th sense of touch is so important and useful to us that we have it all over our body. It's in our hands, and notably in very high sensitivity in our fingertips, but also here, 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 and some pretty important other places. Literally, we're talking head to toe. And David Julius and Ardem Pataputian won the Nobel Prize in Physiology and Medicine for 2021 for their seminal discoveries in understanding how the sense of touch works. So we're going to dive into that, and we're going to see some organic chemistry and even a little bit of physics along the way. You probably have heard in the intro and you've learned yourself that the sense of touch involves a nervous system. Now, a single cell inside a nerve is called a neuron, and we have different kinds of neuron in the nervous system. This diagram shows that we have a sensory neuron, for instance, one that goes from the tip of my finger where I touch something all the way up my arm to my spinal cord, and then that information about touch travels to my brain. That's different than this other kind of neuron, which is called a motor neuron. That sends instructions from the brain to my finger to make it move. And the information about touch is carried in sensory neurons, and it doesn't just tell us what or whether we're touching something, it tells us how that touch is. For instance, it tells us whether what we're touching is soft and furry, or hard and smooth. It might be cold, or it might be hot. Ouch. So you can see that the sense of touch has a very useful purpose to keep us safe in some situations. You've probably also heard that the nervous system works on electricity. So let's take a look at how that works. When we talk about a cell, that's really just a bag full of fluid, and it's contained in this particular thing called a membrane that surrounds it. And the neuron is a very, very long cell, so if you take a close look at this part of it, it would look like a tube. And the inside of the neuron and the outside of the neuron is all water, and in that water is dissolved things called ions. Ions are just atoms which happen to bear a charge. So for instance, table salt, which is sodium chloride, consists of a sodium plus ion and a chloride negative ion. And the remarkable thing about a neuron is that it has an electrical property called membrane polarization. This means that the neuron has excess positively charged ions outside compared to inside. So it carries the power of an electrical battery. Now this picture shows what happens to a neuron when it's at rest, not conveying any information because I haven't touched anything yet. Now when I touch something, then the neuron in action is conveying information, and there's something called an action potential. Oh, did you see that? Oh. Oh, there's another one. What's happening here? You see there's a wave of something that's traveling down the length of the neuron, and that's something that's called a depolarization. It's a disruption of the inherent polarization in the membrane. And if we look very closely at that little local spot on the membrane here, we can see that there are some pores called ion channels in the membrane. Normally at rest, these pores are closed. But during a depolarization, the pores open, and then positive ions, like sodium, flow into the cell, which makes a depolarization, disrupting the inherent membrane polarization. Now, that depolarization has another effect of changing what happens to the channels next door, because these channels happen to be voltage-gated ion channels, which is to say that they sense electrical properties of their surroundings. So the depolarization in one spot will trigger the opening of voltage-gated channels in the adjacent region. So just like a stadium with a hockey game where the fans are doing the wave, there is a wave of depolarization that travels down the neuron length. Now you could think, if I'm touching something, that must have started the wave going. But touching something is not inherently an electrical event. So we can hypothesize that there must be some kind of ion channel that creates a depolarization. This ion channel will be like the voltage-gated ion channel, but instead of sensing electricity, it must sense touch in some kind of way. Well, Paterson and Julius were well qualified to explore and investigate how touch sensing would work because they were experts in electrophysiology, which is a technique that's used to characterize and measure electrical activity of cells. Here's an example of an experiment from the Paterson lab. And here we have some sensory neurons, which we've isolated in a dish, and we've poked them with a very tiny glass rod. We can produce a very, very small poke of 1 micrometer, that's a millionth of a meter, or a larger poke of 5 micrometers. And for the very small pokes, we can look at the electrical current that's flowing through the membrane, and we don't see anything. This dotted line measures 0 current. But for larger pokes, we can see that positive ions are flowing into the cell. So we interpret this as saying that before the poke, the channel is closed, and on poking, the channel responds by opening to let sodium and calcium flow into the cell. This is a pressure-sensing channel, we would imagine. Here's an example of a heat-sensing neuron. And this is an example from the Julius lab, where instead of poking the cells in a dish, we just heat the dish up very gradually from a low temperature to a high temperature. And we do realize that some neurons are different than others. This is an example of a heat-insensitive neuron. It doesn't respond to a temperature change. But here's an example of a heat-sensitive neuron, and you can see that at a certain key temperature, it happens to be about 45 degrees, then the ions start to flow. So there is a heat-sensing channel, we would imagine, inside this neuron. Now the trigger temperature for this neuron is 45 degrees. That's pretty painful. For comparison, a hot tub tops out about 40 degrees, and the hot tap in your faucet at home, which can seriously hurt you, is about 49 degrees. Strangely, if you take this same heat-sensitive neuron and keep the temperature at room temperature, there's another way you can get these channels to open. And that's by applying a certain chemical compound, which is a natural product that Rob Britton would be really interested in seeing. It's called capsaicin, and it comes from chili peppers. This is the ingredient in chili peppers that makes them spicy. And so what's really happening when you eat chili peppers, or if you're unfortunate enough to be in the kitchen cutting a chili pepper and get some on your skin, you will feel a burning sensation. This is a tactile illusion. You see, you're at room temperature, but because you've rubbed some capsaicin on your skin, your brain thinks that there's a fire. Isn't that cool? Actually, it's hot, right? So we believe, or we could hypothesize, knowing this, that not only does this heat-sensing neuron contain a heat-sensing channel, that this same heat-sensing channel could also be a capsaicin-sensing channel. Now, the other kind of expertise that Julius and Paterson brought to this problem was molecular biology, which is the science of how we analyze and manipulate genetic material and genes. All the jobs inside a cell, pretty much all of them, are done by these molecules called proteins, which Dr. Britton did mention. And proteins are made in the cell using information that's carried in these other molecules called RNA. And the information to make that RNA is contained in the genes, which reside in the 23 pairs of chromosomes that you've probably heard about. Those chromosomes are made of another substance called DNA. So we could imagine that out of the about 25,000 genes in our chromosomes, there could be one or two that encode information for making a heat-sensing or pressure-sensing ion channel. And the mission would be to find it. Now, Julius' lab set out to find the heat-sensing channel in the early 1990s, and they reasoned that if you take a look at a heat-sensing neuron and something that wasn't heat-sensing, like a skin cell, which is not a neuron at all, they both contain the same 25,000 genes in their chromosomes. So the thing that makes them different is that only a subset of those genes are used to make RNA for the activity of the cell. Proteins in a heat-sensing neuron would include, putatively, the heat-sensing channel, and there's only about 200 of these which are unique to this particular type of neuron and not found in any other kind of cell. So hopefully they could find, by sorting through this small number of genes, the one that was a heat-sensing channel gene. There are different kinds of tests you can do if you have a candidate gene that you want to test. One is to have a gain-of-function test. You could take the set of RNAs from a neuron and choose a candidate and transfer it into a skin cell. And then you could ask about this modified skin cell, will this now respond to heat? There's another test you can do, which is a loss-of-function test, and that's to take the RNAs in a neuron and eliminate one of the candidates, and then ask this modified neuron, is this neuron now insensitive to heat? And if it is, then the target that you had really was a heat-sensing channel, probably. And finally, you can isolate the protein that, after all, is going to be doing the job and ask whether this protein by itself acts like a heat-sensing channel. And Julius's lab was triumphant at all of these three approaches, and they managed to isolate the gene, which they call TRPV1, out of a collection of technical kind of terminology, which they might shorten to being TRPV1, which they were able to demonstrate was a heat-activated ion channel that also responded to capsaicin. They also used the technique of electron microscopy to solve the structure of the protein at a molecular level. And we can see that a protein, as we know, is made of amino acids that are connected in a long chain. And this chain is folded up in a very complicated structure. But one organizing unit of this structure is this corkscrew-like structure called the helix. And there are numerous helices in the TRPV1 channel, but a certain subset of them are arranged relative to the membrane like nails in a board. So they are going perpendicular to the membrane layer. And that's what keeps the channel anchored in the membrane. Now, the membrane is made up of another kind of molecule called lipids. And all the small lipid molecules are very crowded together, as are the helices in the membrane. And that prevents water or ions from crossing over the membrane. But actually, in the very center of this protein, there are some helices that can move apart to open a pathway for ions to flow. So if we take a look at this particular structure of the channel, it's been stabilized not by raising the temperature, but by adding compounds like capsaicin, which make the channel jammed open. In this case, these two compounds happen to be toxins. One of them is a venom from a spider, and the other one is a venom from the spikes of a cactus. And these two compounds, DKTX and RTX, hold the channel open, and the central helices, which are colored blue, are wide enough for ions to pass through. And you can compare the open and closed channels to see that removing the toxins at room temperature will allow the pinching off of the pathway so that the channel can close. So now we know what parts of the channel are the swinging gates that open and close to regulate the activity of this channel. Now, Pataputian did join the investigation, and Pataputian and Julius, working independently, discovered by similar methods a whole family of related channels which respond to different kinds of temperatures. Some of them respond to extremely hot temperatures, and some of them respond to cold temperatures. And there are certain foods that mimic the responses. For instance, menthol and peppermint, or isothiocyanates in wasabi or mustard, target certain specific kinds of these trip channels to give a sensation. Now, it's not enough just to understand that these things exist, because that was a triumph. But we ought to want to use this information that they exist to see whether they do other kinds of things in our body. And it turns out that two of these channels, TRPV1 and TRPA1, are used for the specific sensation that we call pain. Now, pain is not something that exists outside our body the way that chili peppers do. Pain is something that the brain interprets when it sees that some tissue has been damaged. So what would happen if I hammered my thumb is that some cells would be crushed, and the contents of those cells would send out distress molecules, which would be detected by these so-called nociceptor neurons. These are sensory neurons which can detect these special distress signals, and they contain TRPV1 and TRPA1 channels. Moreover, immune cells, which is called this mast cell, also detects these damage signals, and they secrete these additional signals which will sensitize the TRPV1 and TRPA1 channels, just in the same way that capsaicin, for instance, sensitizes the heat-sensing TRPV1 channel. And the result? Pain. That's an important signal to keep my thumb safe so I don't keep using it. In addition, something else happens. This sensory neuron, which we normally think of as receiving information and passing it to the brain, starts to become an active agent, and it sends out its own messengers that it generates, called neuroinflammation messengers. And these messengers, for instance, go to the blood vessels and make them expand, so that more blood goes to my thumb. That's why it swells up and starts to get red. Other messengers sent by the neuron go to the mast cell, and they encourage the mast cell to keep generating these inflammation signals. So this can go wrong when there's a vicious cycle where immune cells and nociceptor neurons keep encouraging each other to generate these inflammation signals. Even when my thumb is no longer injured, I still may have persistent pain, which we call chronic pain. And there's active investigations of blockers of TRPV1 and TRPA1 to try and alleviate this kind of pain. I'd like to close off by mentioning the piezo channels, and piezo comes from the name for push, that were discovered by Pataputian, because they actually look very different than the trip channels. On the right-hand side, you can see a trip channel for comparison. It looks tiny compared to a piezo channel. The piezo channel, remarkably, has these long, extended appendages that reach out to cover a great deal of membrane, and it has a very curved shape so that it creates a dimpled shape on the membrane, like an upside-down umbrella. Now, this particular structure is of the closed channel because nothing's pressing it. Well, we imagine that when you press the sensory neuron that's sensing pressure, then the membrane would flatten out, and the dimple would then expand the shape of this piezo channel to move the central helices apart so that ions can flow. Last, I'd like to just mention a medical example involving piezo that doesn't involve neurons at all. It turns out that piezo is expressed in blood cells and in other kinds of cells whose job it is to mop up expired blood cells. If you have certain people in the world are born with a variant form of piezo, and one amino acid is missing. There are about 2,800 amino acids in piezo, which are all there. And so this is a very slight functional difference in the channel, which is that it's more sensitive to pressure. So less pressure is needed to open the channel. This is not a grave variation, and there's a slight disadvantage in that you get a little bit more fragile blood cells. But if these people are infected with the malaria parasite, it becomes an advantage, because when a blood cell is infected with one parasite, it will lyse quickly before the parasite has a chance to reproduce. And so you see a pretty high incidence of this variant in populations originating from Africa, where malaria is very common. Ultimately, however, as these people age, they start to encounter a second disadvantage, which is that another kind of cell, which is the macrophage, whose job it is to swallow up and destroy old blood cells, also use piezo, because the act of swallowing requires contacting the destroyed cell, and the macrophages use piezo to regulate this process. Having this variant form of piezo means that the macrophages are hyperactive, and they destroy more blood cells than usual. In response, the body tries to generate many more blood cells, and this creates an imbalance in the way that iron is distributed, since iron is an important element in blood cell function. So these patients, as they age, are in extreme danger from tissue damage because of iron overload. And we can see that screening for this particular genetic variant can help these patients distinguish this particular cause of iron overload from the other kinds of causes of iron overload that could be possible. So in conclusion, I think you can see that it's not enough just to prove that something exists. We can use the fact that we know that it exists to learn something about it. And we can look forward to the knowledge of touch sensing and heat sensing channels that will open many doors to learning about new fields of physiology that we can't anticipate today. Thank you.
Wow, thank you so much. And of course, we're all interested in seeing those doors open. So there have been so many amazing breakthroughs on the horizon with understanding these ion channels. I'm sure our viewers have many questions, and I know there have been a few that have been posted already while you were speaking. So I encourage anyone else who is watching and wants to explore a little bit further and have Edgar respond to your question, please send in a question. Nobel?
We are down to the final presentation of the evening to present this year's Physics Award as it relates to climate science. Our next presenter is Dr. Kirsten Ziegfeld from our Geography Department. Kirsten will highlight the contribution of the 2021 Physics Nobel Prize winners, Manabe, Hasselmann, and Parisi, to the field of climate change and climate modeling, and discuss the role climate models have played in understanding and addressing the climate crisis. Allow me to turn it over now to Dr. Ziegfeld.
Thank you, Nabil. The Nobel Prize in Physics in 2021 was awarded for groundbreaking contributions to our understanding of complex systems. And the one half was shared by Sukuro Manabe, who worked at the Geophysical Fluid Dynamics Laboratory first in Washington, D.C. and then in Princeton, and Klaus Hasselmann, who worked at the Max Planck Institute of Meteorology in Hamburg. And the other half was awarded to Giorgio Parisi. So the half awarded to Manabe and Hasselmann was for the physical modeling of the Earth's climate, quantifying variability and reliably predicting global warming. And the half to Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. And in my presentation here, I will focus largely on the area of research of Manabe and Hasselmann. So first of all, what are complex systems? So complex systems are systems built of components that are interrelated, so they interact. One example is the human body. So we just heard about the nervous system. So the nervous system is one component of the human body. Other components are the respiratory system or the cardiovascular system. And all these systems, they work together in a complex whole to maintain the body healthy. And complex systems are inherently difficult to predict because of the many interactions between components, and they also exhibit some particular characteristics. Some of these are critical thresholds or tipping points, for example. Some others are feedback loops or emergence, or more generally, non-linearity. And I will illustrate some of these examples later on. So now the climate system is another example of such a complex system. The climate system is composed of the atmosphere, the cryosphere, which is everything frozen on the planet, so that would be the large ice sheets on Greenland and Antarctica, or glaciers on our mountains. Then the hydrosphere, that would be the ocean, but also freshwater lakes and rivers. The pedosphere, which is the solid earth, so rocks and soil. And then the biosphere, which comprises all living organisms. And as is illustrated by these arrows on this diagram here, all these components, they interact with each other. So one approach to describing the climate system and predicting its behavior is by climate modeling. So climate models are mathematical descriptions of the climate system. And they span a wide range of complexity, from simple zero-dimensional energy balance models, as illustrated on the left, to very complex three-dimensional general circulation models. So zero-dimensional energy balance models, they represent a planet, such as Earth, as a single point in space, and the temperature of that planet is then calculated as the result of the balance between incoming and outgoing radiation. So this is a fairly simple model that can be solved analytically, which means by writing it down on paper and solving that with, on paper and pencil. These complex three-dimensional general circulation models, the basic idea here is to divide the atmosphere, the Earth's surface, and the ocean into squares, which we call grid boxes, as is illustrated here by this example. And within these grid boxes, we calculate the radiation that is received. For example, we can look at water vapor, we can look at the presence of clouds or of chemical compounds in the atmosphere. And these grid cells also communicate by exchanging energy, water, and chemical compounds. And the work of Manabe and Hasselmann was fundamental to the development of these models. And before I talk about their contribution, let me dive a little bit more into the physical principles that underpin these general circulation models, so these complex climate models. Here, the foundational principles really are the conservation of energy, or the first law of thermodynamics, conservation of momentum, conservation of mass, and the equation of state, which for the atmosphere is expressed by the ideal gas law. And these the conservation of momentum and of mass, this is usually described by what are called the Navier-Stokes equations. So these are very complex equations that we can only solve if we approximate them. And in order to be able to solve these equations, we do need computers. So these are numerical models that can only be solved as on computers. And as I will illustrate later, a lot of progress in climate modeling is also driven by progress in computing. So fundamental contribution of Sukuro Manabe to the field of climate modeling was his design of what is called the radiative convective model of the atmosphere that also includes the water vapor feedback. So the main idea behind this model is to divide the atmosphere into separate layers, and then to calculate the radiation balance in each of these layers by calculating the solar radiation, for example, that is absorbed in this layer, or that travels through this layer, or is reflected. And the same is also true for the infrared radiation that this layer in the atmosphere receives from the surface. And the temperature structure that results from these energy balance calculations is inherently unstable, because now we have cold air that resides on top of warm air. But warm air, because it is less dense and it is lighter, it actually wants to rise up. And this process of air rising up, this is what we call convection. And it is very important because it transports heat, but also water vapor, so humidity from the air surface into higher layers of the atmosphere. And so this, Manabe's model calculates the balance that results both from these radiative processes and from these convective processes. And the major advance that allowed him to also reach some of the most important conclusions from this model is the presence of water vapor and its sensitivity to temperature. So if air is warmer, it is able to hold more water vapor. And we know that water vapor is a greenhouse gas, so it absorbs infrared radiation that is emitted by the surface and contributes to additional warming of these layers. So it is the interplay between all these processes that allowed Manabe to make very important discoveries, such as, for example, the fact that carbon dioxide warms the troposphere, which is the lower level of the atmosphere, and cools the stratosphere. So the stratosphere are those levels in the atmosphere that are higher than about 10 kilometers. So just to give you an idea, if you're on an intercontinental flight, generally you fly at the height, so at the boundary between the tropopause and between the troposphere and the stratosphere. And this result warming of the lower levels of the atmosphere and cooling of the upper levels of the atmosphere, this is also something that has been confirmed with satellite data. So based on this relatively simple model, Manabe, together with his collaborators at GFDL, they went on to build three-dimensional models, first of the atmosphere and then of the combined ocean-atmosphere system. And as you can see here on the right, the geometry of the Earth that they took into account is quite simplified, but they were able to simulate some of the key processes, such as, for example, the influence of ocean circulation on the distribution of surface temperature. And they used these three-dimensional models then to look at the effect of an increased level of carbon dioxide in the atmosphere on climate. And one of their major findings from this type of work is that the warming is amplified at high latitudes. So this is illustrated in this diagram at the bottom left, which shows temperature, which is on the vertical axis as a function of latitude. And these black dots, those are observations. And so as you would expect, so 0 degree latitudes, that's where the equator is, and 90 degrees latitudes, that's the pole. And as you would expect, temperature drops from the equator towards the pole. So now the black solid line, that is the standard temperature that is simulated by this climate model. And then the dashed line, this is what you get when you apply enhanced levels of carbon dioxide to the model. And as you can see, so the difference between the solid and the dashed line increases as you move towards the pole, which is an indication that the warming is amplified at high latitudes. And this is something which we call polar amplification. And and this is a constant characteristics of climate models, which I will again talk about briefly later on. So about 20 years after the design of these first three-dimensional general circulation models, Manabe, together with Stauffer, they made another groundbreaking discovery, which is the fact that the climate system can have two stable equilibrium states, which differ in terms of the ocean circulation in the Atlantic. So what they did is using, again, this coupled ocean atmosphere model, they used different procedures to run this model. And what they found is that there are two possible states of the system, one with and one without ocean circulation in the Atlantic. And this is illustrated by this map here. And if you look carefully, then you see that here in the North Atlantic, where we see all of these isotherms, or line of equal temperature, we see that especially in this area here in the North Atlantic, the model with an active ocean circulation is much warmer than the model without ocean circulation. And so this was the first demonstration that there are multiple possible equilibrium states in the climate system. So this is a very important insight, and a few years later it was realized that if we input fresh water into the North Atlantic, so this could be from ice melting from the Greenland ice sheet, or it could be through rainfall, for example, then we can actually trigger a transition between these different states. And this is illustrated in the diagram here to the right in a conceptual way, which shows here on the vertical axis the strength of the ocean circulation as a function of the freshwater input into the North Atlantic. And what this diagram shows is, so if we follow this solid line here, so this is a state of the Earth system with an active ocean circulation, and then we follow this line to the right. At some point, we hit here a critical threshold, which we call a bifurcation, and then suddenly the system transitions to a stable state without ocean circulation. And this is very important because this mechanism can be invoked to explain some of the abrupt changes that we see in the past in our paleoclimate record. So climate models play a key role in understanding and also predicting how climate will evolve in the future. Since the time of Manabe, so the work that I illustrated last was in the late 1980s, these models have undergone considerable development. So as you see on the left-hand side, the resolution, which is the size of those grid boxes, has decreased substantially by about a factor of 10, which again, it has become possible due to advances in computational power, because these models are very expensive to run. But also, as is shown here in the middle, progressively more and more processes were added to these models. And one key development was the consideration of the carbon cycle. So not only modeling the physical components of the climate system, but also carbon and the cycle of carbon in the system. So what are some of the key applications that we can use these models for? So the first one is attributing observed climate changes to human causes. And it is Hasselmann's fingerprint method, which was published in 1993, which allows us to disentangle the various causes of climate change. And for example, as is shown in this figure here to the left, if we only simulate the the warming that results from natural causes, then we cannot, which is shown by the blue line, then we can actually not reproduce the observed warming, which is shown here in this figure by the black line. But actually, we do need a combination of natural and anthropogenic causes or human-made causes, things like greenhouse gases, particles in the atmosphere, to be able to reproduce the observed warming. And it is work such as this one which has led the Intergovernmental Panel on Climate Change to conclude that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Climate models are also routinely used to make future climate projections. What is shown in this figure here, especially at the bottom, is the regional warming that occurs at different levels of global warming. And again, what this illustrates is this Arctic amplification that I talked about earlier. So here, the different shades of red, they indicate progressively stronger levels of warming. And as you can see in all three cases at the bottom, the warming at high latitudes is amplified relative to the warming in other regions. So finally, a very important discovery over the last decade was the proportional relationship between global warming and the total amount of carbon dioxide emissions, which is illustrated in this figure here. So, if you look at observed warming, and you graph that as a function of carbon dioxide emissions, and also you look at results from future model projections, as is shown by this colored cone, then you recover a linear relationship, which is actually quite remarkable given the nonlinear nature of the climate system. And this is very important because it tells us that every ton of carbon dioxide that we put into the atmosphere adds to global warming, which implies that if we want to stop warming, we also need to stop emitting. And this is really the physical foundation of net zero emission targets, which are now being adopted by many countries and also corporations. So so to conclude, I hope that this presentation helped to illustrate the fundamental work that Manab and Hassaman did to advance the work in the field of climate modeling, and also some of the key contributions these climate models make to our understanding of global warming. Thank you. Thank you, Kirsten. That was very insightful indeed. And I know that many of our viewers are going to be curious to learn more about climate modeling. And it's also exciting to see that there are questions that are coming in right now from our virtual audience. But for now, we'll have to hold on just a little bit longer before we get to read those comments. But do keep them coming. I want to thank all of our faculty presenters tonight from Simon Fraser University for your insightful presentations, your enthusiasm, and of course your passion for science. It's very evident. Before we move on to the questions and comments sent in, I know many of you in the audience today are aspiring scientists yourselves. SFU's programs inspire students to make real-world changes through their work, or from doing a co-op work term to partaking or participating in research projects that ultimately make a difference in our communities. Nabil?
That's correct, Stuart. We hope tonight's presentations inspired our younger audience to become scientists someday. Now it's time to hear from our audience, and we appreciate your participation in these segments. Let's look at those questions and comments you have sent in. So, shall we start with the first question for Dr. Young?
Yes.
Dr. Young, can you talk more about how exactly they can put a gene from the neuron into the skin cell?
Yes. Well, this is something that sounds pretty interesting and intriguing. And in the talk that I gave, we saw an example of just where the scientists were able to take the gene for a heat-sensing channel, for instance, and transform a skin cell into a heat-sensitive cell by this means. Now remember, there are two ways that a gene information can be written. One is in DNA, which is in our chromosomes and is permanently part of a cell. The other way is RNA, which is just an intermediate form that's used to make protein. And if you want to actually put RNA into a cell, well, we actually know, all of us, that really is done, for instance, in the COVID-19 vaccines that many of us have had. That is an example where RNA, which is a temporary form of gene information, is encouraged to enter a cell by enclosing it in a membrane. And when the membrane, which is made of lipid, is encountering the outside surface of the cell, then the lipid molecules gather together and the contents of that particle, which is the RNA, enter the cell. And that's how the Moderna and Pfizer vaccines for COVID-19 introduce the COVID-19 virus gene information temporarily into our body cells. I would stress that it's temporary because RNA has a limited lifetime, and the cell cannot pass that information on to its offspring. So that's one way to do it, but the way that was practically done in this particular instance was to introduce a fragment of the DNA into the skin cell. Now, that can be made to enter the skin cell by the same means as the RNA, but you have to have an additional thing, which is that you then need instructions for the cell to recognize that piece of DNA, and the skin cell needs to know that it normally would not be using that DNA to make the RNA. But we have the ability to synthesize instructions at will for the gene fragment of DNA that we want. And so by attaching that particular instruction, we would fool the skin cell into thinking that particular gene should be used to make RNA temporarily. And again, that DNA is not part of the chromosome, so it could not be inherited by any of the offspring of the skin cell. So temporarily, the skin cell would be fooled into thinking that it was a heat-sensitive cell.
Thank you very much for your answer, Dr. Young. And I think we could switch quickly to Dr. Britton about a very interesting question. Can other amino acids other than proline be used in organocatalysis? Dr. Britton?
Yeah, absolutely. I think in my presentation, I kind of focused on the work that was carried out with proline, but yeah, since 2000, people have looked at all amino acids as catalysts in organocatalytic reactions. They've looked at molecules that are derived from amino acids. They've looked at molecules that look like amino acids but aren't natural. And many of these chiral, naturally occurring molecules have proven to be useful for organocatalysis. And again, I think that really just drives home the point that this chemistry can be carried out by anyone using really cheap, naturally occurring or readily available or readily produced catalysts, such as amino acids.
So, Dr. Zickfeldt, your presentation about the work of climate models and the complexity of it is, I find when I start to delve into it, it's overwhelming. These complex systems are characterized by many feedback loops. What feedback loops play out in climate systems?
So thank you. This is a very interesting question. So I already talked about two of the feedbacks in my presentation. So one is the water vapor feedback that Manabe built into his radiative convective model. So here the idea again being that warm air can hold more water vapor than cold air, and because water vapor is a greenhouse gas, so amplifies the warming of the atmosphere. If we warm the planet, then the air can hold more water vapor, so we have more greenhouse gases in the atmosphere, which then amplifies the warming. Another one that it was illustrated in these in what I call the polar amplification is what is called the ice albedo feedback. So things like snow, ice, they are white, they are bright, so they are very reflective and reflect a large fraction of the incoming sunlight back into space. And so if we warm the planet and the months during which we do have snow on the ground, the number of months during which we have snow cover on the ground decreases, or we melt ice, then the ground becomes darker and absorbs more incoming solar radiation. So, this ice albedo feedback also amplifies the warming. And another one, for example, is a release of carbon dioxide and methane from melting permafrost, because as permafrost melts, some of these organic compounds in the soil can be broken down by bacteria, and the carbon dioxide and methane released into the atmosphere. These are also greenhouse gases, and so amplify the warming further. So there are several other feedback loops, but I will leave it here for now. Thank you.
Well, can I ask you a quick follow-up question? Because I've always been curious to know, well, what role do clouds play?
Yeah, so that is actually an excellent question. So the role of clouds is quite complex, because clouds, on one hand, they reflect incoming sunlight, and this is something we experience when we're out on a cloudy day, and temperatures are cooler than they would be on a sunny day. On the other hand, clouds are made out of water vapor, and water vapor is a greenhouse gas, so they absorb infrared radiation that is emitted by the Earth's surface. So they do have a warming effect. And this is something we experience at night, because cloudy nights are warmer than clear nights. And so the effect of clouds is a balance between these two opposing processes. So in terms of cloud feedbacks, then the question is, with warming, do we get more high clouds, which do have a warming effect, or do we get more low layered clouds, which have a cooling effect? And the latest science indicates that the net effects from clouds on climate is likely positive, which means an amplified warming effect.
Thank you, Dr. Ziegfeld. I will switch back to Dr. Young about this question. What does this understanding of this ion channel do in helping us understand about neuropathies?
Oh, well, now the word neuropathy, in case people are not familiar with it, means disease of a neuron. And we understand in the example, for instance, of chronic pain, that clearly something wrong is happening with the neuron. It's giving out a false alarm where the brain thinks that there's damage, even though the damage has already been resolved. Now, if we know that this neuron is sick, it's one thing to say that it's sick, but what we really want to do is understand what part of the neuron is being disordered. Is it have too much of one thing or too little of one thing? And so that will require identifying the molecules that are different kinds of molecules that are working in the neuron. And so understanding the genes for TRPV1 or TRPA1, for instance, would allow us to tell whether and measure how much, for instance, of the RNA for those particular channels were being produced in the neuron. They would allow us to test how much of the protein was being produced, and they would be able to, we would be able to test what the structures of the protein were in that particular neuron. And maybe they're completely normal, or maybe they're not, but we're not going to know unless we know what molecules to look at. And so by understanding that every kind of behavior of a cell has its basis in molecules, we understand how important it is to know these molecules.
So, Dr. Young, I find that actually quite fascinating, because clearly we're at the very beginning of understanding this, and the way it may lead to opportunities for us to find ways to navigate our way around a condition such as neuropathy.
Yes, in fact, as I mentioned, there are active efforts to discover new compounds, even perhaps natural products, that would be able to either increase or decrease the function of these particular channels. The only way to do that efficiently is if to get a large number of cells to be able to test them. And so knowing these molecules also provides tools to help us investigate function better.
Thanks.
Well, I guess when it comes to these new molecules and the new tools, Dr. Britton will be the expert using asymmetric organocatalysis. Dr. Britton, how does this discovery improve drug research and its cost benefit?
Yeah, that's a really good question. So if you imagine the production of a drug, this is often a very complex process, requires many steps. But at the end of the day, you need an extremely pure final product that will be used to treat humans. And in the past, we've relied very heavily on these transition metal catalysts for reactions. And what we've found is that oftentimes it's quite difficult to remove the trace amounts of that metal from the final drug product. And this can be a real concern because many of these metals are toxic at very, very low levels. And so moving away from metal catalysis allows us to have cleaner reactions and cleaner final products. So it's much easier to remove an organocatalyst from a final product than it is to remove a metal catalyst. And so that's one benefit to using organocatalysis in drug research. With regards to cost, I think, as I already pointed out, many of these catalysts are things that you can buy, at the local grocery store even, by the bottle, and they're not expensive. And so on mass scale, these things are very inexpensive, especially when compared to these earth non-abundant metals that have been traditionally relied upon as catalysts for many of our organic reactions.
Thank you, Dr. Britton. Dr. Ziegfeld, there's a question here that's come up, and it's something that I have been curious about for quite some time. With the addition of carbon to the atmosphere, is it arithmetic on a known rate of incline, or is it logarithmic? I've had different answers about that, and I'm hoping that maybe you have some insight into that.
Yeah. Thanks for this question. So what are you talking about exactly? The effect of warming as a function of carbon dioxide?
Yes. Is temperature rise due to, is it an arithmetic equation or is it logarithmic?
Mm-hmm. So as I showed on my last slide, the temperature, so the warming is actually linearly related to total carbon dioxide emissions. And as I mentioned, this is quite remarkable because we have all these nonlinear things going on in the climate system. So for example, and perhaps this is what you're referring to, the dependence of the radiative effect of carbon dioxide on carbon dioxide is logarithmic. So it declines as we go to higher levels of carbon dioxide. So it levels off. However, the reason why we recover this linear relationship is that we also have a delayed warming in the climate system, which compensates for some of that. So the combined effect is really more of a linear effect, so a straight line that describes the relationship between warming and carbon dioxide emissions.
Once again, demonstrating that these are complex systems, and to be able to understand those complex systems gives us the kinds of insights that we require. Nobel?
Absolutely. Well, speaking of complex, I'm sure Dr. Young would love to explain to us a little bit more on how the capsaicin reaction, that there's a heat sensing ion channel in the neural level, and that similarly it's not the way the brain perceives the signs of touch.
Yes, the brain is really a very, very complex system. I mean, the heart's pretty complicated, but at least you look at the heart and you know what it does. And you look at the brain and you can't see anything. I mean, it's just really gathering all sorts of information from different parts of your body and integrating it into some kind of interpretation. And when we talk about the tactile illusion that capsaicin imitates burning, one idea could be that, well, the brain has two different kinds of information and it just classifies them simply, both as burning. In this kind of picture, you would have one kind of source of information coming to the brain for burning, really fire, and another kind of pathway for information about capsaicin. But the experiment where you take an individual heat-sensing neuron that's different than any other kind of neuron and show that it also responds to capsaicin, and that a heat-insensitive neuron does not respond to capsaicin, that proves that the ability to respond to capsaicin and the ability to respond to heat comes from the same kind of neuron, one pathway to the brain. Furthermore, after you isolate the protein and show that you can open this protein ion channel with heat, and also opened this protein channel with capsaicin without any other proteins around. That's pretty firm evidence that it must be at the level of the sensory neuron that these two kinds of distinct pieces of information overlap and mimic each other.
Thank you, Dr. Young. Dr. Britton, final question to you. Does organocatalysis mimic or mirror the way nature catalyzes reactions?
Yeah, it's a great question. You know, I think I pointed out early on that our proteins are made up of amino acids. And in the active sites of these proteins, we have reactions going on. And some of those reactions involve the amino acids in the protein. And so for sure, it does mimic the way nature catalyzes some reactions. So in several of the slides I showed, we had these things called chiral iminium or chiral enamine molecules, which were essentially the combination of a carbonyl containing molecule and an amino acid. And since those amino acids are found in our proteins, we sometimes have these chiral iminiums and chiral enamines in the inside or the active sites of proteins, and those species then go on and do chemistry or reactions in the proteins or enzymes. And so, yes, organocatalysis certainly mimics the way nature catalyzes reactions, but without the complexity of this massive construct of a protein, just using the one amino acid that does the work maybe inside the protein.
Thank you very much, Dr. Britton. Those were all great questions and fantastic answers from an engaged audience and our three speakers. The engaged audience showing how important the research topics were. Thank you everyone for participating. I wish we had more time to keep discussing all these fabulous topics. Stuart?
Indeed, this was a very inspiring presentation. We didn't get to all of the questions. However, unfortunately, we have come to the end of our program. I want to thank Rob, Edgar, and Kirsten, our three faculty presenters from Simon Fraser University, for their inspiring research presentations. Thank you to you too, Nobel, for co-hosting this event with me. It's been a pleasure working with you and for us to stage this event with the Faculty of Science. I also want to thank Dr. Michael Silverman, the Dean of Science Pro Tem at SFU, for this opportunity to engage the public in scientific research. I think we need more of it. And of course, thank you to you, everyone who joined us in our audience tonight virtually. We appreciate all the questions and comments that were sent in, and I have to apologize that we didn't get to all of them, but we hope to do this again next year to celebrate the next round of Nobel awardees. In the meantime, stay safe, keep healthy, and let's all keep our passion for science and research alive in all of us. Good evening, Nobel, and thank you all. It's been a wonderful evening, and I wish you a great rest of your night.